Okay, hello everyone. So today we are again here for our, I think, eighth lecture on trees. It will be taken by Raghav Goel. So, hello, we are Inter-IIT Competitive Programming Conclave. We are thrilled to unite all the competitive programmers and developers from across 40 IITs, NITs, BITS, and other prestigious universities. Our mission, you all know by now, like, is to ignite the passion in competitive programming, offering the support to beginners. And we are especially excited to announce Algorithm as one of our gold sponsors. Algorithm stands as one of the India's premium platform for internship and placement preparation, specifically designed to help students crack high-end product-based companies. Like their comprehensive programs cover data structures and algorithms, DSA basically development, competitive programming, and extend to projects, resume building, and referrals, ensuring the best possible outcomes, obviously. And Algozenith, even more impressive is their track record. Many of their students, including those from the tier 3 colleges and non-circuitous departments at IITs, have successfully secured positions at top tier companies like Google, Microsoft, etc. So we were also honored to have Vivek Gupta sir in the first lecture of DP. I think you also watched that lecture. And we have another sponsor, 0xPPL. 0xPPL is the Web3 and crypto company. It was founded by Prasna Sankar, who was earlier the founder of Rippling. He was like rank 1 in India in top coder ACM ICPC Google Code Jam at the age of 18. 0xPPL has hired several ICPC world finalists. So if you are one of them, if you are excited about competitive programming, yeah, he has shared his mail ID, prasna@0xppl.com. You can connect to him for the internship opportunities and even if you want to get hired to 0xppl. Now we have our lecturer. Today we will be having the lecture on DP on trees and rerooting DP. It's like one of the most important topic on trees. It will be taken by Raghav Goel. He is currently interning at Google. He's also the candidate master on Codeforces, Guardian on Lead Code, 6-star on CodeSafe. So I'm pretty sure this will be a fun session and you will enjoy the lecture. Also today is Mahi's birthday, and interestingly, I also belong from the same city, half kilometer from his house. So let's enjoy the lecture and we can begin the session. I think. Raghav.
So, hi everyone, I'm Raghav and I will be taking your session for DP on trees. So, please write something in chat. I'm waiting for your uh, messages. Hello, Yashwant. Okay, so in this video, we will discuss about DP on trees, and there are mainly two topics. First of all, you guys have already attended sessions for DP, and I believe you would have done enough practice. And the same thing goes for trees. You might have not done enough practice on trees, but you at least know what are trees and you know things like DFS, BFS on them. So in this class, we will just talk about applying DP on trees. Now we already know the main reason why we apply DP is just uh, to optimize some problems by um, reducing the reluctant part. Actually, it's like if we have a problem and we break down this problem into some sub problems, and among those sub problems there are some uh, problems which are happening in multiple parts. Like this is the repeating sub problem, so we will just try to do it once and try to remember the result so that we can avoid the computation in future. And once we are done with this, then we will talk about rerouting. Now, how many of you have heard about rerouting? This is sort of an advanced concept which you would generally see at the um, Dev 2 D or E level. It maybe come, like it may come in higher level also, but for now we won't be discussing about it in that much depth. Specifically, you can think that if this problem is if a problem from rerouting is coming up at D level, it would be sort of straightforward, which you might be able to solve by just attending the session and solving the problems which I give you for practice. Okay, so I see some people in the chat. Great. Now let's start the session with a very simple problem. Subordinates. This is the very first problem of tree algorithms on CSES. The problem says that we have been given a structure of a company. Your task is to calculate each employee, like for each employee, the number of their subordinates. And we have been given the inputs in a way that for each and every employee, other than the first employee, we will know about their boss. So it's like there are some employees 1, 2, 3, 4, 5, 6, and every employee other than the first one is already the boss or maybe the owner of the company or maybe the CEO. For every other employee, he will have a boss. So it's like for the second employee, the first guy might be the boss. For the third guy, maybe he might also have the first guy as his boss. And then for the fourth, maybe he's having three as his boss, five is having two as his boss, and six is maybe a like directly having one as his boss. So this is the problem, and in this problem, okay, just 1 second. Yeah. So what we will have to do is we will have to tell how many people are subordinates for one, for two, for three, for four, and so on. So for this problem, like we can directly tell that six is not having anyone under him. So six is not having any subordinates. Similarly, five is also not having any subordinates, and the same goes for four. Now for three, three is having 4 as his subordinate because 3 is the boss for 4. So yeah, the guy 3 is having one person under him, that is his subordinate. Similarly for 2, he is having 5 as his subordinate. Now how many people are there as subordinates for 1? Can you guys tell me in chat? I'm waiting for your responses in chat, then we will discuss of what is the case. Okay, somebody directly said n minus 1. And yeah, in this case, it would be actually equal to 5. The thing is, 2, 3, and 6 are directly subordinates of 1, and 4 and 5 are subordinates of its subordinates, and basically they would also be counted as the subordinates of 1. This is something we have in our problem. So we would be given this array in the input, and we will know the number of people. So we will get one integer, that is the number of people, and then this array which will tell about the boss for each and every guy from 2 till n. And then we will have to output this thing as the answer. Does the problem make sense? Just spam yes in the chat if you are with me till now. Okay, great. So let's take one more example. This is this one. There are 5 people. So in the problem statement, n is equal to 5, and the bosses for everyone is 1, 1, 2, 3. Like this is the array. For now, let me call this as maybe just 1 second. I don't know why, but it's not erasing as it should have been. This array of n minus 1 size is this 1, 1, 2, 3. So it signifies that uh, For the employee 1, there will be nobody above him. Okay, so first of all, there are 5 people, and the employees 2 and 3 are having 1 as their boss. 4 is having 2 as his boss, and 5 is having 3 as his boss. And we know under 1 there are 2 and 3, and 4 and 5 are also indirectly under him. So 1 is having 4 subordinates, 2 is having only one subordinate, that is 4, 3 is having only one subordinate, that is 5. 4 and 5 are not having any subordinates. So this is our answer. So now let me show you. Yeah, here in the output we did expect 4110, 41100. That is the answer. Okay, so it might not be very intuitive for some of you, or it, okay, you have actually studied about graphs and actually advanced graphs also, so I think it should now be very intuitive for you. At first I thought that it might not have been intuitive for you, that we can think of these employees as nodes, and in that way we will be able to think of these relationships as edges. Does it make sense? Like right now I'm expecting that I don't need to explain this, that why, how did we think about it. I can say that 1, 2, 3, 4 and 5 are nodes, the employees are nodes, and when I say that 1 is the boss of 2, then maybe I can just say that 1 is pointing to 2 and to 3, 2 is pointing to 4, and 3 is pointing to 5. If I say it like this, does it make sense? I'm waiting for your response. I hope that at least till this point everything should be clear. We have not really discussed anything new. We have just discussed the problem statement, and uh, thinking about the problem statement as a graph or a tree should not be a very new thing. Okay, so since I had to tell that for every employee I have to tell the number of subordinates it has, is not it something like for every person I just have to tell the number of nodes in its subtree other than this node? Like for 1, I have to tell the number of people who are under him, but I don't have to include this node because like in its subtree 1 would also be included, but I only have to tell the number of people who are in its subtree without this. Does it make sense, or did it go over the head? Tell me in chat. Or maybe I can just re-explain. So what I said is, in the problem, what we had to do was tell the number of subordinates of 1, and we know the subordinates of 1 would be the people whom 1 is pointing directly, or the ones who are being pointed indirectly. And all the people who are being pointed directly or indirectly would be coming up in its subtree, but we don't have to count the employee itself. So can I just say that the problem is indirectly asking me to find the, like for every node I have to tell, maybe I can just say answer of I is equal to the number of nodes in the subtree of node I minus 1. Does it make sense? Now the problem has been converted to a very direct problem, where for each and every node we just have to count the number of nodes in its subtree. If we calculate this part, if we are able to calculate this part, then subtracting 1 from it, like for every node, is not a big deal, right? If you could just figure out this part, right? Let me call this thing as sub of I. For the purpose of explanation, I'm calling sub of I as the number of nodes, or maybe I can just call it as, okay, sorry. For now, I can just call it as SZI size, or yeah, I think it's also fine. If I call this as SZ of I, that is the number of nodes in the subtree of node I, or you can just think of it as the size of the subtree of node I. I hope it's fine. Now, you have 2 minutes. Try to think of any way of solving this problem. Like, don't care about the time complexity, don't care about the space complexity. You just have to solve this problem. That's it. Then, how will you do it? You have 2 minutes to think about it. Maybe let me see if I can turn on. Maybe. Okay, I'm just turning on the stopwatch on my mobile phone, and I'm reading the chart till then. On every node, do DFS and count the nodes. Very well, Rudra. That's good. That's the bare minimum I want. Okay. Um, 40 seconds have passed. You have 120 seconds more. Oh, we are having 15 seconds of delay, I guess. So maybe you have 15 more seconds. Make a map of vectors and to the direct subordinates of the nodes in those vectors and apply DP. Um, Direct subordinates. It does not really look good, or maybe I'm not able to understand what you're saying. Post order traversal. It won't matter whether you apply post order, pre order, or in order. And actually, we are not having a binary tree. We are having a normal tree. Uh, so here we don't have anything like post order, pre order, in order. We just have a normal DFS or BFS. DFS memo is nice, great. Using DFS after DFS call DP node is equal to DPIP. Great, that's correct. Okay, time over. Not many people replied. I was expecting more responses. But yeah, the ones who replied, you are absolutely correct. A very simple thing which we can do is, like, we guys already know how to apply DFS, right? You might not apply DP here. Even if you don't apply DP, the problem is still doable. All you need to do is just say, I will go for each and every node. I will maybe run up a for loop from 1 till n, and for each and every node, I will run up a DFS of I. And in the DFS, I will just count the number of nodes I traverse. So if I'm running up a DFS from 1, I will count 5 nodes, right, including this one. Then I can just subtract 1 to get my answer. Does it make sense? Similarly, I can do the same thing for 2, and then for 3, then for 4, then for 5. Every time, just run up a normal DFS, and you will be able to just go down. And let's say you might say that, hey, bro, you created an you created a directed graph here, but I might have created an undirected graph. Even if this was an undirected graph, you still know about the parent for every node. You know that 2 is having 1 as its parent, so you could just still avoid going up by comparing, like by just saying that at whichever node you are going, it should not be equal to parent. And this is something you would have studied in DFS, on how to run up a DFS on an undirected graph or a directed graph. Okay, so guys, are we good to go? Did you understand this approach? It's a very simple one. Let me write this one. So it is sort of a brute force approach, where we say that for each node from 1 till n, let's say each node u from 1 to n, just run up a DFS for every node. That's it. And running up a DFS in the worst case will take big O of n time. We are having n nodes, so it is big O of n square time complexity. You might try to have a small in here just to make, keep things consistent. Uh, okay, so guys, what's up? Are you with me right now? I hope it was not difficult. Just spam yes in the chat if you are with me right now, and if you are not with me, then spam lost in the chat. Just write lost if you are already lost. Okay, so most of the people who have responded are with me, and actually everyone is with me right now. Great. Okay, so now let's see what we are doing. Like, what is the problem in what we have been doing? It might have been intuitive for you that since we have been attending a class DP on trees and we have applied DFS, which belongs to trees, the next thing we are about to do might be related to DP. This thing might be intuitive to you. Okay, so the nodes we had were 1, 2, 3, 4, 5. Now, when you did run a DFS for 2, which nodes did you visit? You visited the node 2, then you went to 4, then you came back to 2 in a DFS. Okay, let me just revise one thing. Uh, when you do a DFS, how do we go? If you are at the node 1, we will first go to a child, then from there you will go to some child, and once you reach a node which does not have any children, basically it is the leaf node, then you come back to the parent, है ना? The recursive function ends and then you come back to the previous function from where you had called it, right? Then you will again come back to the parent because you don't have any more children to visit from node 2. Then you will go to the node 3. Then from 3 you will go to more depth. Once you have reached the complete depth, you will start coming back. I hope you are able to relate DFS with this. Just confirm this thing once, because if you are not able to relate DFS with this thing, then it might be a bit problematic for you. This is not a difficult thing, but it's possible that some people might have never thought of DFS in this way. So now our goal is, like in case of 1, when you wanted to run a DFS from 1, we did go in this way. We did visit all the nodes. Now when we are about to run a DFS for the node 2, are not we just going over the same thing once again? Let's say if we had a tree like this, when you ran a DFS for from the node 1, you went up in this way. When you ran a DFS from 2, you went in this way. Wait, Wait. Everything is repeated. Can you see it? Can you see a repeating sub problem? Guys, just spam yes or no in the chat. Can you see this repeating sub problem? This reminds us of dynamic programming. So now what do you think? What can we store? For the node 1 or for the node 2, like, can we say that when you wanted to know, like, instead of running up a complete DFS in this part, I can just say, like, one will just say to two that, hey, run up your complete DFS and give me the result. I don't want to go through all this stuff. You just go once, like this blue part should happen once, and then whatever result you get, just give it to me. That's it. That's all I care about. So right now we were talking about finding out sz of I, that is the number of nodes in the subtree of a node. So for that, 2 will say that, hey, we are 4 people in this subtree. 1 will say, okay, that's all I care about. I don't really need to go through out in your complete subtree. If I know the number of nodes you have in your subtree, I can say that, like, it's obviously it's possible one might have some more subtrees. In a normal case, one can have some more subtrees and so on. But now one knows that at least I don't need to go to this complete subtree. I can just get the result and that's it. So if the number of nodes in the subtree of 2 were equal to 4, then the number of nodes in the subtree of 1 would be incremented by 4. Like the contribution of this subtree would be equal to 4, right? Oh yeah, let me give one more thing. Let's say uh, this is a tree: C1, C2, C3, C4, and like these are the 4 children for the node 1, and every node is having some subtree in itself. Like they are having some subtrees which may be looking like this or something different. We don't really care about it. If I have to find out the sz of 1, can I say that the size, or basically the number of nodes in the subtree of 1, would be equal to the contribution of this node, the contribution of this subtree, contribution of this subtree, and this subtree. Basically, 1 plus sz of c1 plus sz of c2 plus sz of c3 plus sz of c4. Does it make sense? Yeah, the variable sz which I have taken, basically this name is not so good. Maybe we can refer to as size for now. The size of 1, the size of the subtree 1 of 1 would be equal to 1 plus, like this 1 is coming up because there is one node. The node in itself is just having a contribution of 1. Then the number of nodes in this subtree, this, and this. So we are having sz of 1, 2, 3, like c1, c2, c3, c4 being added up. Are you guys with me right now? Have we got some relation? If you remember, in dynamic programming, what we really like to do is find some recurrence relation and then apply DP. Basically, then do memoization. Isn't it something we really like to do? In dynamic programming, what we generally do is just this thing now. We have some state 1. You try to find out the relation of state 1, basically the answer of state 1. If you already knew about the answers of state 2 and the answer of state 3, and then you figure out what will be the answer for state 1. A very similar thing is happening here. If we knew the answers for the children, we don't really need to go in all that depth, and we will be able to get our answer by just traversing the children, right? So the time complexity for finding out the answer for this node will be equal to the number of nodes. Basically it would be dependent upon the number of child nodes for this node, right? So now the time complexity will be equal to sum of number of children of I, basically the child nodes of I. This will go for all I. What do you think what this value will be equal to? Or if you see, we are just applying a normal DFS. We already know that a normal DFS does have the time complexity of big of n. Or if you think about the time complexity in this way, that we just want to find out the number of child nodes for every node. You know that every node other than the node 1 is a child of someone. So there are, like, the sum will be equal to my n minus 1, which is something we can consider as big of n. So yeah, so we can get the array sz in this way. And if you see, like, calculating sz was good for the explanation purpose, but in reality when you would be solving this problem, you won't be really concerned about finding sz. You can actually directly calculate answer of I, right? When you would be calculating answer of I, the contribution of the child nodes would be just equal to answer of child node plus the contribution of this node, that is plus 1. uh, don't worry if you didn't get it in one way. I just tried to quickly tell you that it's not really necessary to find sz. We can directly find answer, but at the very least we have got one way for solving the problem, that is we can calculate sz and then find the answer. So eventually the thing is, we calculated the relation sz of maybe u equal to 1 plus uh, v belonging to children of I, children of u. Okay, so this is a normal, like, this is a recurrence relation in general format. For any node u, the value of sz will be equal to 1 plus, this 1 is because of the contribution of the node itself, plus the contribution of all the child nodes. Like this part is nothing but taking the contribution from each and every child, and the contribution of every child will be equal to sz of v, where this v will be the child node. Okay, so I see the stream is a, okay, the stream is not having any delay. Great. So guys, just spam cool in the chat if you are with me right now, and maybe LOC in the chat if you are not with me. Okay, there is some delay in the stream. I see one guy is not with me. If you're having any doubt, you can ask if you guys have any doubts. And mostly people are cool. Great. Great. So mostly people understood it. For the ones who did face some problem, you can ask your doubts in the chat. And let me take up a few more similar problems, and then we will see how to code it up once you have formed a relation. Like, I believe it should not be a very difficult thing to code on your own right now, because you have already done a lot of problems on DP and you know about trees also. um, but we will see how to code it up. Like, it's most of the times very simple if you have figured out a very simple relation like this one. And let's say if you had been given a problem where you had to find out uh, This is the question 2. Given a tree, find the not number, GCD of all nodes in its subtree. Okay. So we have been given a tree, and every node will have some value here. It's like you might have some nodes 1, 2, 3, 4, 5, 6, 7, and every node will have some value, maybe like 6, 2, 4, maybe let's say 8 and 12, 4, 3, something like this, maybe 6 ले लेते हैं अगर. So for every node, we will have to find out the GCD in its subtree. Let me directly tell what it would come out to be because it's very direct. Um, so we are having 7 nodes. Sorry, we should have got. Yeah, we are having 7 nodes. 1, 2, 3, 4, 5, 6, and 7. For the subtree of 7, there is only one node. So the GCD is just 8 directly. For 6, the GCD is 4 because there is only one node in the subtree. So its GCD would be equal to the node itself. The GCD of the node 5 is 6. For the node 4, it is 3. Now, the GCD for the subtree of node 3 will include these 3 nodes. So what should be the GCD of all of these nodes? 12, 3, and 6. The GCD will come out to be 3. Um, I hope it's already fine, but still, let me tell. By GCD, I'm talking about greatest common divisor. And many people might have heard of it as HCF, highest common factor. So, like when we want to find out the GCD of 12, 3, and 6, 3 is the biggest divisor which divides all these 3 numbers. Now, for the GCD of the node, for the sub, oh, sorry, this was the GCD for the subtree of 2. 3 was for, okay, 3 will come here, and for the subtree of the node 3, there are these 3 nodes 2, 4, and 8. The GCD will come out to be 2 because it is the biggest number which can divide everything. And for the node 1, there are so many nodes in its subtree. Will we go to each and every node to calculate what is the GCD of all of these nodes? Guys, what do you think? Tell me in chat. We know that the GCD for the node 1 will come up to be 1 because the GCD of all of these numbers is just 1. But how will you calculate it? Will you go to each and every node? Try to write some relation in the same way as we did here. Try to think about a relation here. You have 2 minutes. The more you think on your own, the better it is. Okay, great. One guy said GCD of 1, 2, and 3. I believe you are saying the GCD of the nodes 1, 2, and 3. The values are actually again 1, 2, 3. G of node is equal to GCD of node and GIT. Very well, Shubham, exactly. And Shri Janya also said, yeah, almost correct. Like instead of saying node and child, you should have been saying GCD of node and child. But it's correct. Yeah, Naim also said the correct thing. Great. So I think it should be more intuitive than the last time now. That instead of going into the subtrees in the DFS, You can just say for the node 1, its GCD would be the GCD of this node, these nodes, and these nodes, right? Like you have to figure out the GCD of all of these nodes. You can just break it down into these three parts. The GCD of all of these nodes, which you already have, like the value of the GCD of all of these nodes, is something you have already calculated and it is already stored here. Similarly, for all of these nodes, you have already calculated their GCD and have stored it here. So you can say the GCD of this node, and this node. Just take the GCD of all of these three values and you will get the GCD for the complete subtree. So relation is coming up to be something like GCD for the node U is equal to the GCD of um, the value of node U. Remember, we had some values for each and every node. So the value for the node U, comma, um, and like there is sort of GCD of V1 where V1 is the first child, GCD of V2 where V2 is the second child, and so on. So we will just take the GCD of all of the children and the current node, the current value, and take the GCD of all of these things. If you notice, it is very similar to, like, the relations we are forming are very similar to what we used to do in dynamic programming. We are just assuming whenever we want to find the answer for some node, you are just assuming that you already know the answer for its children. Take it in this way: whenever you want to calculate the answer for a node U, if it's having some children v1 v2 v3, and you want to find out some information for the subtree of node U, okay, in that case you are assuming that you already know about the answers for the subtrees of nodes v1 v2 and v3, and you want to calculate your current answer, that is the GCD of U, using the information GCD of v1, GCD of v2, GCD of v3, and for every node you are already having the values, like value of u1 and value of v1 and all everything. In some cases you might have to use something like value of v1 as well, okay, in the relation, and feel free to use it, there is no problem in it, right? The main goal is you should be able to calculate your answer for the current node using information from the children nodes only and the current node. There should be no other nodes. If you are involving only these nodes, then your time complexity will be big of n for all of these nodes, and sometimes you might have some, like in the relation you might have some stuff being done which requires some logarithmic factor as well, maybe if you're finding max or min. Like, let's not complicate it for now, uh, but I hope that you have got some good idea. Now once again, if you are good to go till now with me, oh yeah, one more thing: what will be the time complexity here, guys? What will be the time complexity? What do you think? It would be a little different from the last time. As a reminder, uh, whenever you have a function GCD of a comma b, it takes big of log n, like log of minimum of a comma b time complexity. Okay, big of n log n. Yeah, actually it should not have been n log n, it should have been big of n log a, where a is the largest value, but yeah, it's fine, you got the main idea. We will have a logarithmic factor, and in some cases it might be even less than this. It might actually be less than big of n log a. Mm, like mathematically calculating the time complexity might actually prove that it should be big of n. I'm not sure about it, but it is. something similar to big O of n and then logarithmic factor, it is already pretty good. Okay, so once again, just write cool in the chat if you are with me. If you have lost somewhere, then just write look, and you can ask your doubts. And let's try to go a bit faster now. If we go a bit faster, then we can discuss more things. Yeah, tonight we have a Codeforces contest and it is rated. Okay, let's go on. So the time complexity here is something like big O of n log a. I believe that we can even remove the log a factor, but for now, even if you say that the time complexity is something like this, it's fine. And for the space complexity, we are just having n states. If you think about your states, this GCD of any node, like you can create an array with name GCD and have a size n, or maybe you can just name it as G or DP or like whatever you want to name. So we will have n states. So the time complexity here will come up to be big O of n. Okay, great. Now let me pick up a question 3. This should not take a lot of time now. You're having, like, you are being given a tree, and for every node, find the depth of its subtree. Yeah, the problem is pretty straightforward. You will be given a tree, maybe something like this, and you will have to tell the depth of the subtree for every node. So like we are having 7 nodes once again, 1 2 3 4 5 6 7. The depth of the node 7 is, okay, just 1 second. The depth of the node 7 is 1, right? When I say that the depth of a subtree, I'm talking about something like this. For the node 5, how many nodes can you visit if you're just going down? It might not be a very good definition, or maybe, yeah, you can define it in this way also. Or maybe just say that uh, how many nodes can you traverse when starting from 5 and going into its subtree, and you go like the longest path. Maybe you can just say the longest path in the subtree of 5 when you're starting from 5. There are many ways of defining depth. I believe that at the very least you have got the idea what I mean by depth. So if I'm talking about the depth of the subtree of 3, then it would be, because of this path, equal to 4, right? So the depth of 6 is going to be equal to 2 from 6 to 7. From 5 it would be 1 2 3. For the node 4, the depth is just 1 because there is only one node. For the node 3, the depth is 1 2 3 4. um, wait, just 1 second, let me see if this stream is going on. Yeah, my pen is visible. Okay, so for the node 2, the depth is just 1, and for the node 1, the depth is equal to 5. I hope the problem is clear. Guys, you have 2 minutes. Just give me the relation directly. Let's say we will name these states as dp of I, or maybe depth of u. I want you guys to tell me about the relation for finding out depth of u only using uh, the answer for the child subtrees, and some constants maybe, like basically whatever be the contribution of the current node and the contribution of the subtrees. Okay, depth of node is equal to 1 of depth plus child. Great, at least it's close. Depth of node is equal to maximum of depth plus of child plus 1. um, yeah, great. Srijanya, it's a good answer. You guys still have a minute. D of node is equal to maximum of D of node comma 1 plus D of IT. Great, that's a good answer. Great, most of you got it good. So the thing is, if you look at any node U, and let's say it is having three children v1, v2, v3, for finding out the maximum depth, either that depth would be coming up from this subtree, or from this subtree, or from this subtree, right? The contribution of the current node would always be equal to 1 for the depth of the subtree. It does not matter in which path you go, but you will go either in this path or this path or this path. So you would like to have the maximum of these three, right? You would like to have the maximum contribution from these. So depth of u should be equal to 1. This 1 is coming up because of the contribution of the current node, plus the maximum of depth of v, where this v will be a child of u. Sorry, I'm not able to write with good handwriting, but I hope it's readable. Shall we go ahead? The time complexity here should be just big O of n, and the space complexity should also be just big O of n. How do we need to initialize the DP array within 1? Um, See, it's up to you with what value you initialize these values. I generally prefer to initialize like in this case I want to find out the maximum, like I want to find out the maximum depth, right? So I generally prefer to initialize things with the minimum possible value. So in this case I would prefer to initialize with 0 in general, because I generally have a dummy node. If you don't have any dummy nodes, then you can directly initialize with 1. uh, but apart from it, when I will start to calculate these values, at that time I will initialize the nodes with this value. Like maybe you can just forget about it. Just forget about it, because without much context it might look something stupid. Depth of u, like the initial value I would recommend you to have is equal to uh, the contribution of the current node. Let's say instead of finding the depth, if I was asking you to find out the farthest node, the distance to the farthest node from this node in its subtree, in that case the contribution of this node would have been 0. then in that case I would have been initializing depth of u with 0. But in this case, when I am having the contribution of the current node as 1, then I will initialize the depth of u with the value 1. Okay, so guys, shall we move on? Now this one is a good problem. What we have to do is, like, again we are given a tree, and what we need to do is find the uh, sum of distances. Actually, this is something for each node u. You have to find out the sum of distances to all the nodes in the subtree of node u. So it goes like, if you are having a tree, maybe like 1 2 3 4 5 6 7, then the sum of all distances, like the sum of distances to all the nodes from 1, should be equal to 1 plus 1 plus 2 plus 2 plus 2 plus 2, because there are 4 nodes at distances of 2 and 2 nodes at the distances of 1. So the answer will come up to be 8 and 2, that is 10. Similarly, for the node 2, there are 2 nodes in its subtree which are at distances of 1 1. So the answer will be 2 for the node 2. And actually, like, there are 3 nodes in the subtree of 2, but one of them is the node itself, that is 2, which is having a distance of 0. So you can maybe just say that it is plus 0, which will just still have the same value. So is the problem clear what we have to do? Now I want you guys to find out a relation here, and let me tell you, it is a bit more difficult than the previous problems, assuming that you are studying DP on trees for the very first time, or maybe you are not having a very good experience with dynamic programming. But if you have solved enough problems in DP, then this might not be very difficult. So for now, let me just give you a good enough hint. Let's say answer of u is the answer for the node u, basically uh, sum of distances to all the nodes in the subtree of u, and you have to calculate this value for each and every node. And as a hint, like, this part is the hint, we will require this information also, the number of nodes in the subtree of node u. Maybe let me just call this as count of u, count of nodes in the subtree of u. You guys already know how to calculate this thing, though it would have been a good problem for you to try on your own, but for now we are having limited time and I wanted to discuss this problem. So I have given this big hint that for calculating this thing for every node, you will actually require this state. You can easily calculate this one, like we already saw how to calculate it. So you guys are having like 5 minutes, or maybe we can have We can have a 10 minutes break, and you will give your, like, you will have your attendance in this time as well. You can mark your attendance, and like, we are having a 10 minutes break. We will meet at 5:17 p.m. And till that time, try to think of a relation on your own, on how can you find out answer with the help of this note. Like, you will actually use this. So yeah, um, do both these things, attendance and try to think about it. You have 10 minutes break. So, did you guys think about something? Um,
So, did you guys think about something?
Sorry, but the session might go a bit longer. I think I should have been a bit faster. Okay, I'm waiting for the responses in the chat. Are you guys back? Oh, others will come. Let's start. Okay. Okay, so guys, the session might go a bit longer because I forgot that I do have to code it live as well. So it might take a few more minutes. Okay. Okay, so I hope that you try to think about something. So let's say if the tree is looking like this, and you want to find out the answer of 1, we have already understood that you will have 3 components. The first one will be the contribution of the current node in this answer, which would be just 0 because the distance from the current node 1 to 1 is just 0, plus the distance from 1 to all of these nodes, which is something you have like not calculated yet. You have calculated the distance of all the nodes in the subtree from them till 2, but you want to find out the sum of distances from all these nodes till 1, right? Like what you know right now is, if you see, this answer of u is nothing but the sum of the distances from u till v, where v belongs to the subtree of u, right? So right now, when you say answer of 2, it is nothing but the distance, like the sum of distance of all the nodes v, like the distance between all the nodes. Oh, sorry, I said it wrong. The distance, the sum of distances from 2 to all the nodes in the subtree of 2, right? Sorry for speaking wrong thing in between. Okay, so you know this thing, and while calculating answer of 1, you want the distance of v to 1, not till u, not till 2, right? You want the contribution of this subtree, but just answer of 2 is not enough, है ना? And if you see distance of, like for all the nodes in this subtree, you want their sum of distances to 1 instead of 2. So what you want is sum of distances of all the nodes v coming up in the subtree of 2, their distance to 1 instead of 2. And this thing, like this specific thing for each and every node in the subtree of 2, would be actually equal to distance of that node till 2 plus 1, right? Now when I'm telling, looking at this might feel a bit complicated. It is because I'm just writing things mathematically. so that you don't get some wrong idea from what I'm speaking. But when you try to think about it on your own, like maybe after the class, you will see it's not really complicated. I'm just saying that for every node in the subtree of this subtree, their distance from 1 is actually 1 more than their distance from 2. Because if you want to go from any node till 1, you can just say that I will go till the node 2, and then from there I just have to go one step forward. So can I say this thing? Try to think about it and tell me, does it look good? And once you get this, now you can just say that this plus 1 would be coming up for each and every node in the subtree of 2. How many nodes are there in the subtree of node 2? There are count 2 number of nodes. So the contribution of this subtree in answer of 1 would be equal to the answer of 2, and for each and every node you would have got a plus 1. Like if you just remove this plus 1 every from everywhere, then this is nothing but the sum of uh, sum of distances of all the nodes from 2. So that will become answer of 2 plus count of 2. Mathematically it might be looking a bit complicated to some people, but if you just think about it logically, it's very simple. I'm just saying that for all the nodes in the subtree of 2, from there go till the node 2, and then you would have got count of 2 number of nodes here. Then all these nodes will go one step above to reach the node 1. So you already know about the cost for all the nodes to reach to the node 2, that is nothing but answer of 2. And then going up one step up, will have a cost of 1 per node. There are count 2 number of nodes, so total cost will be this much for each and every, like for all the nodes in the subtree of the sub of 2. Similarly, you are having this child subtree. So for answer of 1 you have got 0 plus answer of 2 plus count of 2, plus similarly you would have got answer of 3 plus count of 3, and that's it. So if you try to write it in a general form, basically if you try to write a recurrence relation, it would be answer of u is equal to um, the contribution of the current node, which is just 0, plus uh, for every subtree, for or basically you can just say for every child node of u, the contribution of their subtree would be equal to answer of v plus count of v, right? So this is gonna be the complete cost. Basically this is gonna be the recurrence relation. Since we have got the recurrence relation, we can code it very easily. I have been saying this thing again and again, that after getting a recurrence relation, coding is very simple. Now I will show you how I like to code, and it's gonna be simple. So for now, let's talk about time and space complexities. And actually, like when I talk about time and space complexities, again I think that it might not be that simple for you to just determine the time or space complexity by looking at the recurrence relation, specifically because I'm the one who has written it. But when I will talk about the code after that, talking about time and space would be very simple. It would come to be big often, but I will first write the code and then you will be able to see it yourself. Okay, so shall we go to code? Just write code in the chat if you want me to go to code, or if you have some doubts, then just write your doubts directly. Like don't write this word, instead write the specific doubt you have. After the attendance, mostly people went out. Okay, someone is saying rerouting first. Actually, it would be better to first of all discuss about the code, like how to write code, and then we can go to rerouting. And by the way, writing code is not a difficult task. Even if I don't discuss this, you guys would still be able to code it, but I'm just willing to make things a bit simpler. Okay, first of all, tell me that the font is large enough now. Let me see on my screen. Okay, so on my mobile screen, I can see it clearly. It should be good for all of you also. Um, so in general, what happens is we do get to know about the number of nodes in that tree, and then we generally create an adjacency list, assuming that we will be given some edges as the inputs. Let's say we have been given n minus 1 edges in the inputs. Fine. I hope that you have already seen something like this on how we take the tree as input. We are just having n minus 1 edges being given in the input. Let's assume that it is in this way. And you can notice that I have created a one based indexing, like I have created a tree with one based indexing, because it will have some convenience. Like right now, the nodes we are having are 1 till n, and the node at the zero based, at the index 0, like we are having a node at the index 0, right? So this is a dummy node. So we already had been given a tree, है ना? We would always have a node, we would always have a tree. Generally, while applying a DFS traversal, we have a node and we have its parent in, like whenever you are traversing a tree, you will have its parent in the as the second parameter. So if in a zero based indexing traversal, you have, like you generally say that your node 0 is the root and its parent is minus 1. But I feel it to be more convenient to think of the node at the, like node 1 as the root and the dummy node at the dummy node to be its parent. So I will have a dummy node here, and it's up to you. Like you don't really need to follow me this much. If you want, you can have zero based indexing. It's fine. I just wanted to give you some idea that why do I like one based indexing. And I believe that if you're coming up till this topic, DP on trees, then you guys already know about lambda functions. If you don't know about lambda functions, you can just create normal functions. You can just create normal functions like them. But for now, I will create lambda functions, which look something like this. You write function, then the return type. So if you have something like int DFS with int node and int parent, let's say something like this, you will write a lambda function as function of the return type that is int and the parameters that are int and int, and then the name, and then something like this. If you don't know of what is going on, then uh, you can just search it on internet. You will find some GFG link. Okay, let me see what is the problem here. Okay, the return type can be written something like this, and you don't really need to worry that much. For now, for this class, we would always have void as the return type, and we are just writing function in this way. Okay? And most importantly, syntax is not the main problem here. Or maybe for now, I can just actually create normal functions. I will show you why I like lambda functions as well. For now, we will have a void, and we will pass the adjacency list. So I hope you already know that how we apply the normal DFS. We just go to each and every child and then say that, hey, apply a DFS for the child, and um, if the child is equal to the parent, then continue. है ना? This is a normal DFS. I hope we are good to go till this point. Now the difference, like while applying DP, what we will do is for each and every node, we would like to have something, है ना? Like in this case, we would like to have an integer. Right now, I'm coding the first problem where we had to find out the number of nodes in its uh, subtree for each and every node. So we will have a vector of int sz array of size n plus 1. For now, I'm initializing it with 0. That is the neutral value. है ना? Like, it's up to you. Whatever value you want, you can just initialize it with anything. And we would be calling a DFS function. Where 1 is the root and 0 is the dummy node which I'm passing. And I would like to have this array sz being passed up. है ना? So I will initialize sz, like the part which I was discussing at some point of time, that whatever state I have, I always like to initialize it with the normal value. Like if it does not have any children, just having the contribution of the node itself, then what will be the value here? By the way, this is the problem where we have to find out the number of nodes and the subtree for each and every node. So if for every node you want to find out the number of nodes and its subtree, one part would be just the contribution of the node itself, which is 1. Then for each and every subtree, you will have their contributions. है ना? So we will come to this part later on. But at the beginning, you will have the contribution of the current node. So it's coming up to be 1 in this case. That's why I'm initializing sz of the node as 1. After that, we want to get the contribution for each and every node, each and every child node. We have already been iterating over the child nodes, and at the point where you would have already iterated, like you would have already done the DFS traversal, the answer for the child node would have already been calculated, right? So its contribution is nothing but size of c1, है ना? So you can just say sz of node plus equal to sz of child, है ना? We have just uh, added the contribution of the child subtree like this. That's it. Now guys, tell me, does it make sense? If you look at the DFS, like if you just leave everything else, currently the main concern for us was DFS traversal. So this was the normal DFS traversal. We had one, oh, okay, yeah, this is the normal DFS traversal. In our case, we had applied DP to store this state size. So all we did was include a vector of integer size, because every value will be just like the value of every state would be just an integer. So we are having a vector of integer size which is being passed in the DFS, and we initialized its value and added the contribution of the child subtrees. That's it. So please write cool in the chat if it makes sense. If you are with me, just write cool in the chat. And if it went over the head, then maybe write LOC. Change from white to int. Okay, so somebody is saying that why don't I convert it to an integer, and then in that case I can just say something like this. I believe that this is your concern. But the thing is, Like this would also work, and it's totally fine if you do it in this way. Now the way in which I have been doing, okay, sorry, if you write it like this, then you will have to write return sz of node also. But this is something I do prefer, that always keep it void. Then I will never have to think whether I have to pass pair of integers or an integer or anything else. And I just create a vector of integer for keeping the values of those states. It's totally up to you if you want to pass on an integer, and like if I discuss it, it would be a waste of time because it's just based on your preference. What is the extension you are using that pops up the syntax errors? I think it's with the name of code lens. I will look at it at the end. I believe it should be something like code lens, which is popping out all these errors. Okay, great. So let's talk about the other problems. Like if you had to find out the GCD of all the nodes, then what would it be? You could just initialize the, like in that case, you would have something like a vector of integers val as well for each and every node, which you would have been passing. For the second problem where you had to find out the GCD of all the nodes, in that case, you would have oh, you would have a vector of integers val with you. So okay, let me just remove it for now. We don't really need to call the DFS function. We are just talking about how the DFS function will look like. So in that case, you would have something like, let's say, for now I'm just giving the normal name DP, or maybe I can just give the normal name answer. So you will say answer of node initial, like while initializing you could just say answer of node is equal to answer of value of node, and while adding the contribution of the child subtrees you could just say answer of node is equal to GCD of answer of node and answer of the child. Answer of child is actually already having the GCD of all the nodes in the child subtree. And similarly, for calculating the maximum depth, for like for the problem which we discussed with maximum depth, you would be initializing answer of node with 1 because uh, the contribution of the current sub node there was 1. The contribution was coming up to be 1, right? And we were taking the max of all this. Basically you could just write it as this also, depth of u. Like right now the relation is not looking very good. A better way of writing this relation would be depth of u is equal to the maximum of 1 comma maximum of depth of v plus 1, and this max will go over v for all the child nodes. This is a better way of writing the relation. uh, like you could have done it in the other way also. You could have just added plus 1 at the end and find this first, or you can write it in this way. All this is saying is for every node, like either you will have only this node, then the contribution is 1, or if you go to any of the child subtrees, then you will have this complete path which is going to be equal to the answer of this node plus this one. And like both of these are equivalent. Okay, both of these are equivalent. It's up to you which one you like to write and the way you like to write the code. And answer of child plus 1. So your DFS function would have been looking like this in that case. um, yeah, by the way, as a reminder, I'm not really spending a lot of time at the code part. So just in case if you feel that you're not able to keep up with me right now, it's fine. I'm just willing to give you some idea of how I convert those relations into code. Like in my head, I will first of all think about the relation, and then while writing code, how am I writing them? So this is just to give you some idea. It's fine if you're not able to keep up with me right now. You can spend some time after the session on your own. That will be the time where you actually learn. For the last problem which we had done till now, where um, the relation was looking like this. Obviously, when you are using this count of v for finding answer, you would need to have this, like you will have some relation for the count array also. So you will need to write a relation for count also. Count of u will be equal to 1 plus the sum of count of v, where you already know that the v is the child subtree. Okay? Sorry, the child nodes. So now we are having two states here, answer and count. So we will have to parse these two things, answer and count. And in the normal DFS, like what are the default values for answer and count? You see, answer will have a default value of 0, the contribution of the current node. And in case of count, you're having 1 as the default answer. So answer node is equal to 0 and count of node is equal to 1. And the contribution of the child subtrees for answer is answer of v plus count of v, basically the answer of child plus the count of child. So answer of node plus equal to answer of child plus count of child, right? And for count of node, it's just the count of child in the contribution, right? So this is also done, and you can see how simple it is. Okay, now let me look at the chat, guys. We, like from my side, I believe that we are done with the DP on trees part. Now it's time for the second part, that is rerouting. It would be, it won't be very difficult, but it might be a bit difficult for you to imagine in your head for the first time, but it should be fine. For now, just write cool or Luke in the chat. Basically, just give me a sign that I should go on. Okay. You guys can have 2 minutes break, because there might have been a lot of things for you to digest in the last couple of minutes where I had been coding in front of you. So you can have 2 minutes of break, and let me read the chat till then. Please do a simple try run on small tree with rerouting. Uh, yeah, in case of rerouting, I will do some small dry run, simple dry run. Okay, so yeah, so guys, would you like to have rerouting in this class itself, or would you like to have a separate session? I see that most of the people are gone, so that is why I'm considering this as an idea that maybe we can have another session, and then I will be able to spend more time for rerouting part. Right now, I will have to teach it in a hurry, which I don't really feel to be very good. Can you, in the meantime, what was the extension? Yeah, so I'm just asking to you guys, what would you like to have? Would you like to have a separate class for rerouting or just extension here? And yeah, for the ones who are asking about the extension, I believe it should be code lens. No, it's not code lens. Then what? Oh, sorry, error lens. Error lens. My bad. Not code lens. It is error lens. Okay, so I think mostly people are asking to cover it in this class itself. Okay. Yeah, then let's go. Let's keep it in this class itself. Now also good. Yeah, great. That would be really good then. So let's start rerouting. So the name rerouting, like just look at the name, rerouting. What do you think? What would happen in it? Yeah. So let's say if there is a tree like 1, 2, 3, 4, 5, 6, 7, and 1 is the root right now. And then I say change the root from 1 to 2. The tree will look like this then. 5, 6, 7, and 1 is having two children, 3 and 4. Right. The root has been changed. We have rerouted the tree. Now 2 is the root. This process is known as rerouting. And it's not so complicated if you see. Like whatever children 2 had, they will still be its children. Whatever children 1 had other than this node which has become the root, 1 will still have all the other children, and for all the other nodes apart from 1 and 2, their subtrees will not change, right? The subtrees will change only for the node 2 and for the node 1. 1 has lost the subtree of 2 from its subtree, and 2 has gained the this subtree which 1 had without 2, right? That's the only change we have got, right? So where can it be useful? Like this is what we have in rerouting. Now why do we use it? The thing is, let's say if we have a problem like given a tree, and our task is to determine for each node the sum of distances from that node to all the other nodes. So this is the question 5 and the first question for rerouting. Given a tree, then in that for each node find the sum of distances from that node to all the other nodes. This is the problem. I hope it makes sense. It might be looking a bit similar to the fourth problem. The difference is, in the fourth problem, we were finding the distance to all the nodes in its subtree. In its subtree. That was happening in the fourth problem. But now we are not talking only about the subtree, but we are talking about all the other nodes. Let's say if the tree is looking like this, then for the node 1, okay, so again, luckily we are having the 7 nodes. Like every time I drew the tree, I never intentionally had 7 nodes, but at the end I realized that I'm every time having 7 nodes. Something is strange here. Okay, so apart from jokes, if you see earlier for the node 2, like if you just talk about the node 2, please go off. Yeah, if you talk about the node 2, earlier it was having only these 3 nodes in its subtree, so the sum of distances was 0 plus 1 plus 1, that is 2. But now in this case, it will have to find out the sum of distances to all the other nodes, that is 0 1 1 1 2 2 3. That is too much. Okay, it's 10. I hope it's 10. 1 2 3 6. Yeah, it's 10. And the similarly you will just find out the sum of distances to all the other nodes. Again, if you just had to do this problem without caring about time and space complexities, you could have run up a normal DFS from each and every node, while which will cover the complete tree, and it will work. But we have to do it in a bit more optimal way, right? And there is one thing which I would like you to pay some attention to, that for the root node, the complete tree is its subtree. Can you notice this? Write in chat. For the root node, the complete tree is its subtree. Unfortunately, the stream is lagging behind, I think. Fine, just to calculate for one node, then for its subtree we intervals and... Okay, you guys can see it, right? For the root node, the complete tree is its subtree. So if you just did this problem in the exact same way as we did earlier, if you just did the exact same things, you will get the answer for the root node, right? For now, let's call it as sub answer, subtree answer basically. So sub answer of 1 will be equal to 0, that is the contribution of the node itself, plus summation of v belonging to the child of u, sub answer of v plus count of v, right? You will just in this way find out sub answer, that is the exact same thing which we did earlier in the question 4, and then you can say the answer for 1, which is the root, is equal to the sum answer for 1 right now. है ना? Everything is good till now. Can you guess what will be the next thing we do? Guys, tell me in chat. Can you guys guess what will be the next thing we can do? Yeah, by the way, DP on trees, which we discussed earlier, only works when you are talking about subtrees. When you are talking about finding something in its subtrees. If you have something like this where you want to find out um, some information for every node to all the nodes, then normal DP with like DP on trace will not work. Great. Pratik, have you ever learned from me, Pratik? Have you ever attended any of my sessions earlier? Because you are exactly giving, like you are giving the exact same answers which I was expecting. What we can do is find the answer of child in terms of parent. Find the answer of child in terms of parent. Hmm. Okay, so you're saying that for this note, find out the answer if this was the parent. Yeah, this is something I see some people doing in rerouting, something like this. But I feel that the way which I will teach here is a lot simpler than that. Like a lot simpler than the thing which I have seen other people teaching. So the way I do rerouting is, if you want to make 2 as the new root, like like whichever node will be the root, whatever value of sub answer for that node you have will be actually equal to the answer, है ना? So what I generally prefer to do is, oh my bad, I want to get to this situation, right? I want 2 to become the new root. Earlier my root was this, and now I want this node to become the root. So the thing which I do is, I break this edge. I just assume that let's break this edge. If I break this edge, in that case, the tree will look like the intermediate situation, like tree. Maybe you can just say it as intermediate tree. During the transformation will look like this. And like the array which you had created earlier, this sub answer, the state which you had created and the other state count which you had created, for these nodes, like whatever subtree they have, their subtrees will still remain the same even when you break this edge. So their values will not change. The same thing goes for this, the same thing goes for this, and even for this node. When you move from this to this subtree, or maybe you can call it as a forest, it will not change. The only thing which will change is the uh, values on the states for this node, because it has lost a subtree. Earlier, at some point of time, I would have said that count of 1 is like I would have incremented count of 2 in count of 1, and I would have incremented um, sub answer of 2 plus count of 2 in sub answer of 1, है ना? This is something I would have added as a contribution when 2 was a child of 1. But now I'm saying that 2 is not a child of 1. 2 is a separate thing. There is no edge in between. If it would have actually been the case, in that case, I would like to just revert this. Earlier, the changes which I had made, I just want to make them, like I just want to cancel them out. So what I can do is, for canceling these changes out, I can say that, hey, just subtract the things which you had added earlier. They will cancel out each other. Sub answer of 2 plus sub answer, sorry, count of 2. Just cancel out these changes. Now can I say that after performing these 2 changes, it is like I have reached this situation. But what I want is 1 should be a child of 2. So I can, like, if you see this relation I had earlier, the relation which I had formed earlier was like this is the contribution of a child for the parent, है ना? Now what I want is 2 should be the parent and 1 should be the child. So something like this should happen. Count of 2 should be incremented by count of 1, and sub answer of 2 should be incremented by count of, or actually you can just to stay consistent, write it as sub answer of 1 plus count of 1. है ना? After performing these two steps, oops, I moved it. Okay, got it back. Yeah, after performing this, I would be at this stage, right? I will be in this stage in that case. So now I know how can I do the rerouting process. If you look at it, it is nothing but this is something similar to removing an edge, removing a child. It is something like I can say remove child, the parent which is 1 and the child which was 2. है ना? Maybe I can just call this as a function remove child 1 comma 2. It will remove 2 as a child from 1, and I can call this as add child 2 comma 1. It will remove 2, sorry, it will remove 1 from being a child of 2. Sorry, it will add 1 to be a child of 2. And I do like to call this complete process as change root from 1 to 2. Like these are the names of the functions I like to create. Name this as change root 1 comma 2. Name these functions as these. So after just performing this function, my tree from this will become this, and now the values of sub answer and count for each and every state will actually have the values for their current subtrees which they have right now. So now what I can do is I can just change the roots one by one and make all the nodes become the root one by one. So eventually, like you will change the roots n minus 1 times. So after changing the roots n minus 1 time, changing the root is taking just big of 1 time every time. So basically having big of n time for the whole process of changing the roots and making some nodes become the root one by one. I will be able to make every node one by one as the root. And earlier, the pre-calculation which I had done to calculate the values of sub answer and child for every node and count for every node, it would have also taken big of n time. This is the pre-calculation part where we had been calculating the DP states. Calculation where we calculated the DP states. The next part is rerouting, where we make every node become the root one by one. All the nodes become the root one by one. And in this process, in this part of making every node become the root one by one, we will have to do one more thing. Once your node 2 becomes the root, you will have to update the answer for 2 as the sub answer of 2. Since it is taking just big of one time every time, it won't really cause much trouble. For every node, you will have just big of one time being added, so it's fine. But in case if it was something like having logarithmic factor here, then the time complexity would have been something like big of n log n. Uh, you will be able to figure it out on your own also. Like calculating time complexity is not a very big deal. So maybe you can have 2-3 minutes for digesting what we have studied just now, and let me read the chat till then. Okay, Pratik, you said a very good thing. Since the operations, like when we had oh my bad. Um, like this was the way we added the note. So at the time of removing the child, since it since this part has to be the inverse of this, um, keeping the orders in the other way around makes sense. But right now it is not causing any trouble. Right now, like these two things are independent of each other. They don't have any dependency on each other, so it's fine. But yeah, in some problems it does happen that when like the states depend upon each other, you will have to um, like you had this as the second step while adding the note, so it should be coming first while removing the child. So yeah, that thing will happen in some complicated problems like the one which I will give you as homework. um, okay, so somebody is asking that when we go to the okay, somebody is asking that from 1 when we went to 2, now when we have to go from 2 to 3, according to you the answer will change, but I have a claim it will never change. uh, so basically what I want to say is, when you made 2 as the root from 1, did anything else change? No, there was no problem in any of the other states. Every state is still having the exact same thing it should have earlier. Like if um count of 5 was supposed to know about the number of nodes in the subtree of 5, it will still have the exact same information in it. And that same thing goes for all the other nodes, all of these nodes which were not a part of rerouting. The only two things which were a part of rerouting were 2 and 1. And we did keep this thing in mind that when one loses 2 as a child, the states of 1, both the states count and sub answer, should have the values which they would have if 2 was never a child of 1, है ना? So yeah, for the node 1 as well, the states are still having the exact same things which they should have had if 2 was never a child. And for 2, you have added this, you have added the contribution of this. So 2 is also having the exact same states it should have if it was the root. So now it does not matter how many times you change the root and which way you choose the you change the roots. At any point of time for the tree, the states would always be valid. So your concern that if we have like if we make 2 as the root once, then we at some point of time make 3 as the root, nothing will be a problem. Like you will just go in this way. At first 1 is the root, then you will make 2 as the root, then from 2 you can just make 5 as the root, then from 5 you can make 2 as the root once again, then 6, then 2, then 7, then 2, then 1, then 3, then 1, then 4, then 1, है ना? Maybe just in simple words you can just have sort of a DFS for going on to each and every node to make it as the root. I hope your doubt is cleared. If your doubt was something else, then please mention it in chat. Okay, yeah, your doubt is cleared. And is anybody having any doubt? Anybody else having any doubts? I hope nobody thought about it in this way, that if I have to make 5 or 6 as the root, then I will directly make them. That's not going to happen. Like in this process which we had been doing, we were just breaking an edge, and like, let's say if the edge was in this way earlier, pointing out to 2 that 1 is the parent and 2 is the root, we just broke it and added it in the other way. But if you want to make 6 as the root, then a lot of things will change. You can't directly make 6 as the root from 1. You will have to go it in order or think about some other way. Okay, any doubts? Yeah, right now the DFS operation which we are applying, uh, initially we had a DFS for pre-calculation, and then we are having a DFS for rerouting, and both the times we were having just some constant time operations, so the time complexities remain to be big often. But some, like, we won't always have constant time operations. Sometimes we might have maybe some multi-sets in the states for every node, so the time complexities can vary, they can be different. um, Pratik, I didn't really get your question directly. Like, uh, maybe let me read it again. Hey, DFS and recursive is not very intuitive to me, but why recursive? Um, See, it's up to you. In which, like, whether you want to keep things recursive or in whichever way you want. The main thing which I want to um uh, tell right now is, the main idea here is that whenever a node becomes the root, if all of the deep if all of the states which we had created earlier are having the same values which they should have, basically if they are having the number of nodes for count, the number of, like, for the state count of 2, if it is having the number of nodes in its subtree, and similarly for sub answer, if it is also having the value which it was supposed to have, basically the sum of all of the nodes in its subtree, then in that case, the root node, like for the root node, sub answer and answer will be the same, because the subtree is covering the complete tree. Now, if I could somehow make each and every node become the root one by one, then I will be able to get the answer for each and every node. And whenever I want to change the root from one node to another node, I just have to apply two operations one by one, basically two functions, this add child and remove child, which are having some constant time operations. So I can change the root and big off one time, right? Now the idea which I'm saying is that I can apply a DFS to one by one go to each and every node and change the root. So basically each and every node will become the root one by one, and I will just uh, remember the value of, like, I will just find out answer of that node, because I will know about the sub answer for that node. Now You don't really need to do it in the exact same way. You can have your own methods. You can do it in any way you want. But remember one thing, whenever we are talking about changing the root in this big of one operation thing, the root should be transferred to a node which is directly connected. If you want to change the root to some other node, I don't think it can be transferred this easily. I think I'm clear. Okay, so did you get it, or do you have any other doubts? Sorry in case if I got something wrong from your doubt. And yeah, just as a disclaimer, once, you don't really need to follow the exact same steps which I have told you. This is for everyone. Do it in any way, but just try to grasp the main idea which I'm trying to say. And for rerouting, there is some other way as well which people use. You can, if you want, you can watch Karthik Arora's DP on Tree series. It is a really good one. It is very famous on YouTube as well, so you can search that one. And yeah, you should definitely try to solve the CSES problems on the trees section. I will actually mark all the problems which I'm asking you to do, which you can do with DP on trees. Okay, and yeah, now we can just go to code this problem. And before going to code, let me tell you about the problems which I believe you should definitely try. Um, yeah, so the first problem is subordinates, though we have already discussed this, but you should definitely code this up on your own. This is a problem on DP on trees. This is, I think, also a problem on DP on trees. I did it long ago, I don't remember now. Then this tree diameter problem. There is one very simple way of solving this problem, which you would have studied whenever you study about theory. But with DP on trees as well, you can definitely solve it. And you should try this problem out after the session. And then this problem, tree distance is one. We will code it right now. We have already discussed the logic. Or maybe I can just show you the code directly. We can save time if I just show you the code directly. And then this is the problem. Oh, sorry. Uh, tree distances one is the problem which I'm giving you as homework. You have to attempt this. And tree distances two is the problem which I will show you now. Like we have discussed the logic and I will show you the code. And this is related to binary lifting. Let's skip it for now. Okay, so you have to do the problem still deep or tree distances two. Please give some sums on DP on trees. Huh? Discuss one with code. Okay, so guys, tell me one thing. Do you want me to discuss the code which I have already submitted earlier, or do you want me to code it up right now? I'm fine with both things. Though coding is something you will have to do on your own, so even if I code it live, it won't really create much difference. Maybe we can just directly code it. Okay, so somebody is asking, please give some sums on DP on trees, but I'm not really able to understand what are you asking for. Sorry. Code it up, make me understand the flows better. Yeah, that's one thing which I really like about coding life. Okay, so this is just my personal preference that first of all, I don't like to create functions like this. I like to create lambda functions while coding it up. Now I will actually like to show you the way I code problems related to trees and for rerouting. I think it's a bit simpler. So the very first thing is uh, I like to create lambda functions, and you will be able to see the reason very soon. Um, So you can already see that I do have an adjacency list, but I don't have to pass it here because the function which I'm creating here can already access this as soon as I'm having this sign, or if I write this. Like, you can study about lambda functions if you don't know about the variables we can access, or for now you can like, just for simplicity, you can just have this uh, ampersand sign here, so that you will be able to access everything which is declared here in the block space, in the block scope. And yeah, remember one thing, we are accessing them by reference, so if you change some value here, the values outside would also be changed. And we do need a vector of integers count of size n plus 1. We do need a vector of long sub answer of size n plus 1, and an answer vector of size n plus 1. So initially we will just count the uh, pre-calculate, like we will just pre-calculate the values for DP states. So count of node would be just 1, the contribution of the current node, and sub answer for node would be 0. And then we will go for each and every node in the children array. If child is not equal to parent, then, oh sorry, just in case if I had written it incorrectly above, please see it. If the child and parent are equal, only then we will continue. Oh yeah, so this is the normal DFS function. If you see, we have just written a normal DFS function where we are not calculating anything. This is the place where we are initializing the states for the current node, and then we can write the code for adding the um, contribution of child subtrees of nodes of child subtrees. But for now, I would like to write it in this way: add child, where I pass a node and a child. And basically, I will just write the code which I was about to write here. Instead, I will just write it here and then call that function. It's up to you. If you want, you can just write it here also. So count of node should be um, uh, you can just see what I'm doing. The contribution of the child nodes for the current node would be this now. We are just doing the exact same thing which we would have written here. And similarly, we will have a function remove child also, in which I will just do the exact opposite. I will just cancel out what I had done earlier. Now, like in this case, the order doesn't matter, but sometimes the order will matter if there is some dependency between these two uh, states among themselves. Right now, there is no dependency among themselves, so the order does not matter. And there will be one more function, change root, where I will have I will just remove the child first. Uh, This would no more be the child of the node earlier, and then add the child in the other way. Maybe we could have written it in this way, or it's fine. Okay, so there will be another function, reroute int parent. So at first we will um, initialize answer, basically answer of node, and apart from it we will have the normal DFS running up. If child is equal to parent, then just continue, otherwise change the root from node to child, then do the rerouting process from child where the node is the parent, and eventually when the whole subtree of the child node would be done, then you would again make the current node as the parent, as a root. And for the part of initialization, this is the condition which we had found earlier, that answer of node will be equal to the sub answer of node, right? So most of the times the thing is, this this code will remain the same. Like if you look at the DFS function, apart from these two lines which I have removed, this will always remain the same. We will just add 1-2 lines depending upon the uh, states you have created. You will just initialize them here, and in the rerouting process, other than the line which I have removed, all this code will remain the same, and this change root function will also remain the same. You will just create this add child function once, on the basis of the recurrence relation which we would have formed. Like we did form this recurrence relation, like not this one, but yeah, we did form a recurrence relation. So on the basis of the recurrence relation you formed, you would have created this add child function, and you will just create a remove child function which should cancel out these two lines. Like whatever you did here in the add child function, it should be cancelled out by the remove child function. If you can't remove it, maybe if at some place you had something like, um, you were having maybe, let's say, a state max, and you said mx of node is equal to max of mx node and mx of child, so you can't really cancel it out here, है ना? In that case, that is where you might have to use something like multiset of integers. Sorry, it should be vector of multiset of integers, where you would be inserting things. Maybe like you will insert something out, uh, maybe like mx of child dot r begin to find out the maximum value, and you would remove it here. You would be removing the contribution. Oh, sorry. You would just remove the contribution here, and I know. So for this problem, we don't have it to be this complicated, but in the homework problems, you will have to do something like this if you are applying DP on trees. Or maybe think about some other way. There are some other ways as well. The one which I told you is something I felt to be intuitive when I did the problem for the very first time. Now let me look at the chat. It might have been looking a bit complicated because we really did create many functions here. Um Code it up, it makes me understand the flow better. We can work with local variables. Oh, pass by value can't be done in lambda functions. You can pass by value in the lambda functions also. If you say something like this, then all the variables outside would be passed by reference, but this is a very bad thing. And oh yeah, one more thing. You can't edit them. If you pass them by value, you can't edit them inside. Or it might be possible in some other way, but I'm not really sure. To be honest, I mostly times use this by reference only. I don't remember the last time when I would have used it by value. What is auto doing here in the lambda function declaration? Okay, so one way of declaring lambda functions is like this, but we programmers are lazy people. Would you really like to write it in this way, or just write it like this? When you have the auto declaration, you don't really need to write all this, but with the auto declaration, like let's say if I say auto here, I can't use the recurrence here. I can't call the function itself, um, because if I'm calling the function itself, then it is like I'm saying auto x is equal to 10 plus x, but it does not know what is this x, so it won't work. And you can study about lambda functions on your own. There are ways of having auto declaration and having recursion as well. Maybe like this. People write it like this also. In this way, you can have recursion. Okay, so anybody having any doubts? I think we are almost good to go, or maybe good to end the session. Oh, no doubts. What about others? Oh, and by the way, did you enjoy the session? Did you feel the session was good? I'm not sure, but I think there should be some feedback form as well, so you can just fill it out, or maybe just directly text me on Codeforces or LinkedIn, wherever you want. For those who don't know about me, when like just search, um, it's Raghav. Like this is my code. Oops, this is my Codeforces profile. So if you want, you can just message me there also, or you can search Raghav Goel on LinkedIn, and I'm an SW at Google, so just sorry, SW intern at Google, so just apply the filter, you will find me. Okay, so let me just confirm if there is anything left. For the topic, we are done. Okay, so